Okay, one handy thing that we can use these lists of bond energies for is to estimate the enthalpy of a reaction. So here's another way that we can get enthalpy for a reaction is to use bond energy values from a table or given in a question. Okay, and the formula is the enthalpy for a reaction, help if I could draw her up here, is equal to the sum of the bond energies of the reactants minus the sum of the bond energy of the products. Okay, and instead of remembering that formula, you can just remember the difference between the two and decide if it's negative or positive. Or have a look at this. Okay, so we've got our reactants on our left, we've got our products on the right. Okay, and so individual gaseous atoms they're going to share, and so here we've got our bond energies for our reactants, and here we've got our bond energies for our products. Okay, now to go up this way, why did I just erase? But to go up this way and down this way, we're going to need our, this way is going to be positive and this way is going to be negative. So we need to take the bond energy for the reactants going this way, and in the positive, and then the negative this way. All right. Have I got those? I think I should have done the arrows that way in my diagram. Anyway, it's the difference between the two. Okay. So here, for example, I've got, what I was just talking about in the last video, I've got hydrogen peroxide decomposing to water and oxygen. Okay, there's my balanced equation. I've given you little symbols for each. And what's the enthalpy for this reaction? Okay. So the easiest type of thing to do here is to look at what bonds are broken and what bonds are made. Okay. So on the left-hand side, we've got two molecules, so we have to break an oxygen-oxygen bond in each one. So we're breaking two oxygen-oxygen bonds, and we can look that up in a table. And each of those is 146 kilojoules per mole. And we're going to be breaking the four OH bonds, which are 463 kilojoules per mole. So add them all together, and we get the total of 2144. Okay. And the bonds made on the right-hand side, we need to make four oxygen-hydrogen bonds, so two for each water. And we're going to make an OO double bond. Okay, we're not going to multiply it by two, but we look in the table for the double bond, and it gives us at 498 kilojoules per mole. Okay, so don't multiply it by two. You'll see it's not equal to 2 times the singular bond energy. So just look up the double energy, and we add those all together, and we get 2350. So the bonds energies in the reactants, or the bonds broken, negative 206, and, negative, so what do we got? We got 2144 positive minus 2350 gives negative 206 kilojoules per mole. Okay. All right. So here we're going to do something. So we're going to do the same problem now, but we're going to, so we worked it out using bond energies negative 206, but we're going to calculate the enthalpy of the reaction using heat of formation values, okay? So the enthalpy using heat of formation values is going to equal the sum of the heat of formation of the products minus the sum of the heat of formation of the reactants. Okay, so we're working out the same problem two different ways. Okay, so the products is going to be 2 times the heat of formation of water plus 1 times the heat of formation of oxygen minus the heat of formation of the reactants is 2 times the heat of formation of H2O2. Okay. So hopefully I've given you these values. So 2 times the heat of formation of water is negative 285 kilojoules per mole. Plus the heat of formation of oxygen, or oxygen's already at its standard temperature and pressure. So that's plus 0. Minus 2 times the heat of formation of H2O2 is negative 285 kilojoules per mole, And let's put it in our calculator and see what we get. 2 times negative 285. Oh, help if I turn my calculator on. 2 times negative 285. And then I've got plus 2 times 285. Oh, you know what? I was going to say that's going to equal 0. I've done this wrong. The heat of formation of H2O2, what a duffer, is negative 191. Okay, let's try. Let's see if I've got my calculator on. I've got the right value. I think I should be okay. 2 times negative 285. And then negative 2 times negative, so that's positive 2 times 191. And I get negative 188. Okay, so we solve the same problem 2 different times. So the enthalpy for the reaction, we solved it using bond energies here, and we got negative 206 kilojoules per mole. And then we solved it using heat of formation values, and we got negative 188 kilojoules per mole. So it's about 10% out. Okay, what's going on? Hess says they should be the same no matter what path, but they're not. Okay, let's get there. So the enthalpies calculated via the method of using the bond energies are always an estimation, okay? As bond energies differ slightly in different molecules, okay? The values in the bond energy tables are averages of these bonds between these atoms in all molecules with that type of bond. Okay, big words there, what do you mean? Okay, the carbon-chlorine bond energy is listed here as negative 339, as 339 kilojoules per mole, okay? That's an average of every molecule that we can measure the bond energy of a carbon-chlorine bond. It's the average of all of them, okay? But, for example, in each different molecule, it's slightly different than that, okay? It's not always the average. It could be the average, but it could be slightly up or down. So for example, here I've got a methane backbone, so 1 carbon there, and 1 chlorine there. So I've got 1 carbon to chlorine bond and 3 carbon to hydrogen bonds. And in this molecule, it's 351 kilojoules per mole. It's higher than the average. Okay. Here now I've got 2 of them underneath it. I've changed it slightly, and each one of these bonds is less. It's 337 kilojoules per mole each, not 339. And here, in this one, I've got 3 of them, and they're 320 each. So it differs slightly depending on the atoms around it. And there's no way to calculate it. We need to measure it. But what you need to appreciate is that the number that we finally put in the table is an average of all these. Okay? So when you're looking at a table for bond energies, and you're using those bond energies to calculate the enthalpy, it's just an estimate. Okay? So this second one that we did... the first one that we did here was an estimate of the enthalpy, and we got negative 206. And it's a decent estimate because if we use the more accurate value using the heat of formations, we get negative 188. So it's an extra 10% out. That's not too bad for an estimate. Okay, so that's why we use estimations for enthalpies using bond energies, because the bond energies are all slightly different for different molecules, and we take the average of all those different situations. Okay, let's do an example. Use bond energies to estimate, the enthalpy of the reaction between ethene, chlorine to produce dichloroethane. So we're starting with ethene, C2H4, and we're adding chlorine, and we're ending up with dichloroethane, which is C2H4Cl2 gas. Okay, and you can see here that we're all balanced, so we haven't got any stoichiometry. So what we can do is just estimate. Okay, so add the bond energies in the products and the reactants and see what we get. Okay, so I'm going to expand these out, and you should be able to do this by now. Oh, hold on. Look at me saying you should be able to do it and make an error. next year it'll help out because you'll know the structures of these more. But you can probably intuitively guess these structures and how many bonds there are, to say it properly. Okay, now it doesn't matter where you have it, but they're the bonds there. I've drawn them in. Okay, so we've got 1 carbon-to-carbon double bond and 4 carbon-to-hydrogen single bonds. And here we've got 1 chlorine to chlorine. Here we've got 1 carbon-to-carbon, 2 carbon to chlorine, and 4 carbon to hydrogen. Okay, now what I'm going to do is look at my table. A carbon-to-carbon double bond in C2H4 is this one, 610 kilojoules per mole. And carbon-hydrogen, there it is, 413 each. I'll write times 4 there. And 1 chlorine to chlorine, where's that? Down the bottom there, 242. Okay, and my products, I've got 1 carbon-to-carbon single, 348, and 2 carbon chlorines, 339 from my table, and 4 carbon hydrogens, 4 times 400, 413. Okay. Now, it's the bond, I'm trying to remember the right way around. Bond energy of the reactants minus the products. Okay. So the total for the reactants is 610 plus 4 times 413 plus 242, 2504 minus products, 348 plus 339 times 2, not too late, plus 4 times 413, 2678 kilojoules per mole. Okay, so 2504 minus 2678 negative 174 kilojoules per mole is the enthalpy for that reaction. Now there's something that a few people might recognize here is this. There's a few bonds in these molecules that didn't change. The 4 carbon-to-hydrogen bonds were there at the beginning and there at the end. So there's another way where you can do it and just class it as the bonds broken minus the bonds made, okay? Because any bonds that remain unchanged would have been in both sides of the equation, okay? So we had 4 times 413, and then we minused away 4 times 413, so it didn't really matter. So another way you can approach these, I look at bonds actually broken versus bonds made as well, rather than a total bond energy. Okay, let's do another one. We've got a reaction between chloromethane. So you can see that hydrogen and chlorine only forms one single covalent bond, so carbon must be the center there. So you can get that structure fairly easy. And methanol, the same type of thing. Hydrogen forms one bond, and we can see that they've got an OH. It's hinting at the structure there. Oh, I should draw a bond in there, shouldn't I? OH, okay. So chloromethane and water to produce it. Oh, what a duffer. Teaches me to reading it. And water, and I'm going to draw water like this to show its bond, produce methanol. Now I'll draw my methanol. And hydrogen chloride. Okay, let's do it the easy way. Let's do bonds broken. Bonds made. Because there's 3 carbon-hydrogen bonds that are not going to change, okay? So I'm going to draw these, maybe in red, okay? what we're doing is we're breaking that bond and we're breaking that bond. Okay. The OH is now going to bond with the carbon, so we're making that one. All right. And we're also making that hydrogen chlorine bond there. Okay. So a bit trickier to do, but once you get the handle of it, it's all good. So the bonds broken is one CL bond, or a carbon chlorine bond, and one OH bond. And the bond made is a carbon to oxygen bond and one hydrogen chlorine bond here. Oh, okay. I'll change colours and I'll look it up. So a carbon chlorine bond is 339. And an oxygen hydrogen bond, trust it. Oh no, there it is, 463. I was thinking it might not be on the table. A CO bond. Oh, look, we've got a different... Oh, let's just choose one. It's not going to be like in CO2. It's going to be... Oh, the triple bond. It's the single bond. It's this one over here. See, the CO in CO2 is a double bond, and the CO in carbon monoxide is a triple bond. But we've only got a single bond. So it's 358 kilojoules. And have we got a HCl in here? We do, 432. Okay. So, our enthalpy is going to equal the bonds broken, 339 plus 463, minus the sum of the bonds made, 358 plus 432 kilojoules per mole. And I'll put it in my calculator. 339 plus 463 minus 358 minus 432. 12. Positive 12 kilojoules per mole. Alright. I think I've got another example here. Alright, let's do another one. Use the bond energies to estimate the heat of combustion of hydrazine. Okay, so we're talking about a combustion. The products of the combustion are nitrogen gas and water. Okay. N2H4. Hydrogen forms single bonds. Oh, why am I drawing a carbon there? Nitrogen likes to form 3 bonds. So we've got this molecule. Gas and O2. Gas, nitrogen gas and water. Okay, let's make sure that we're balanced. So there's 4 hydrogens, so I need a 2 there. Okay. Oh, I think I might be balanced. 2 nitrogens, 4 hydrogens, 2 oxygens. All right, so there's my balanced equation. Okay, use bond energies to estimate the... All right, I think we're pretty much breaking every bond, aren't we? Yeah, we're pretty much breaking every bond. Okay. Nothing's remaining the same. So we're breaking 4 times nitrogen and hydrogen. Alright, break here. And 1 times nitrogen, single nitrogen. Have we got the value for that? We might not have the value for that. Oh no, it's there. Good. Phew. And 1 times that O2 bond is a double bond, okay? Oh, look, they've got it over here too. Okay, and here we're forming an N triple bond, okay, with the N2. And we're forming, in the two waters, we're forming 4 OH bonds, okay? So, our enthalpy, our estimate for our enthalpy is going to equal 4 times the nitrogen hydrogen. There it is, 391. Plus a nitrogen single bond nitrogen, 163. Oh, hold on, I've closed my brackets off. What was it? 4 times 391 plus the 1 nitrogen, which is 163, plus my O2 bond is 498. minus my products. And N in N2 is 945. Nice, a lot of energy in that triple bond, a big value there. And 4 times oxygen, hydrogen. Where's the oxygen, hydrogen hiding? Oh, over here, 463. Put it in our calculator. 4 times 391 plus 163 plus 498 minus 945 minus 4 times 463 negative 572 kilojoules per mole is my estimate from bond energies. Look at part B here, even though I haven't labelled it part B. Determine the more accurate heat of combustion for hydrazine using the heat of formation values. So our enthalpy, or our heat of combustion, is going to equal a sum of the heat of formation of our products minus the sum of the heat of formation of our reactants. Okay. So it's going to equal, big brackets, our heat of formation, what of our products, N2, plus our heat of formation of, 2 times the heat of formation of water, a razor, plus 2 times the heat of formation of water, minus the heat of formation of hydrazine, N2H4, plus the heat of formation of O2. Simplifying it out, should I change colours? I feel like a changing colour. I'm going to get the heat of formation of N2 is 0. That's how nitrogen exists by itself. 0 plus 2 times the heat of formation of water, which is plus 2 times negative 285 kilojoules per mole. The heat of formation of hydrazine is given to us there, 95, and the heat of formation of oxygen is 0. So what do we got? We got 2 times negative 285 minus 95. So it equals negative 665 kilojoules per mole. Okay, so this, using the heat of formation, was the more accurate value. Okay, we know from the processes and learning about it, negative 665 kilojoules per mole. Our estimate came out at 572, so we're more than 10% out there using bond energies. All right, there's some examples from the textbook, and I'll leave you with that work too, and we're finished the chapter.